a lot of systems. He did his PhD with Peter Wolf, and then he moved to Princeton, and later on he moved to Stanford. So he's a very recognized researcher on topological systems, and he's going to give a quantum meeting, an informal talk about model building for flatband phenomena. And also he will deliver another talk as a FIS seminar next 6th of October. He's around if you want to discuss, or I don't know, whatever you want to do, he's available for some discussion. Okay, so thank you very much. Thank you for coming and for this talk.
Thank you, Rosa, for inviting me. Is the recording okay?
Yeah, I think it's okay. Yeah, it's now recording.
Okay.
Yes.
So, so first of all, please excuse my delay. I tried to find parking, and a few days ago when I visited Rosa, it was easy, so I thought it's easy as well, but apparently it was not. So sorry for the delay. In the course of the next days, I will give 2 talks, so I try to arrange material that is sufficiently orthogonal such that you can appreciate both of them and don't feel as if it's repetitive in any way. And the first talk I picked is derived from several currents in modern condensed matter physics, which all, for some reason, evolves around flatband phenomena. A flatband, what would people think of this? A flatband would just mean that you have a continuous spectrum of energy eigenstates that, as a function of momentum, would not change in value. That's, technically speaking, a flat band. And there's different limits in which a flat band is trivial and limits in which a flat band is non-trivial. Think, for instance, of a metal, and just think for yourself as if you're taking the atoms apart and say, increase the distance between the atoms by the factor of 10. Obviously, the tunneling amplitude will decrease. Let's even say it's basically 0. When the tunneling amplitude decreases, you would get a flat band technically. You still have translation symmetry, and all the energies would be independent of momentum, would be at one level. But this is obviously a trivial flat band limit. But what you'll see in this talk is systems where you have a high tunneling amplitude, and still the system develops either exactly flat bands or nearly flat bands. And the introduction I'll give revolves around the question, how flat is flat and which part? And you'll see in a second why I chose this question. So basically, when people think about a flat band, it would imply that the band should be flat over the entire Brinner zone. But when you make it a little bit broader, the scope, and you ask yourself, okay, I'm already happy when certain parts of the bands is basically flat, and that would already give you an interesting impact on the ensuing many-body phases, because flat means a large density of states at that energy. So maybe we can already find interesting phenomena just from a fraction of the Brinner zone being flat. I'll come to this later. I'll give you one example where flatness plays a role, but sort of finite flatness in certain points in the Brinner zone, and this is Kagome metals. Kagome refers to a lattice. I'll come to that, and I'll show you what happens there. It is one of the most discussed condensed matter topics in the past 5-6 years. The materials were discovered in 2019, and since then it has been intensely discussed. For instance, many scientists in Donostia also actively work on this. Like, that's sort of, I think that's the center for Kagome metals research in Spain right now. The other thing that I want to hint at, maybe I'll quickly go over it if we have time, is some new theoretical concept that came up in the past 2 years. It's called higher order van Hove phenomena. First of all, we need, of course, to understand what a Van Hove phenomenon is. You know, the Van Hove singularities in a band. We'll discuss that at the example of the cargo metals, and I'll keep an eye on the time. So if we have time, I'll go into this and tell you about higher order Van Hove phenomena. But then I want to go to yet another direction where flat bands play a role. You heard of twisted materials, where they basically take two layers and they slightly twist the angle against each other. And that's one mechanism devised by Alan McDonald from Texas, by which you can make a band very flat. There was a lot of activity in this field. It's called twisted materials right now, twisted transition metal dichalcogenides, twisted bilayer graphene. And one of the main contributors to this used to be in Barcelona, if I'm not mistaken, Dmitry Efetov. He moved to Germany. Well, for us, fortunately, maybe for you, unfortunately, he moved to Munich. Anyways, if we were to sum up what is currently going on in condensed matter physics, I would say twisted materials and cargo metals are among the most actively discussed fields. That's why I chose them. Before we go into medias res, let me just start with this introduction and get you a little bit more sensibilized towards what I mean by the question, how flat is flat and which part? I can use this right there. So let's, for the moment, let me just draw a diagram. And on the x-axis, maybe I should adjust the labeling a little. I mean, I'm counting how much of the Brillouin zone is flat. So when I say all momenta k star with a property that the derivative of the dispersion relation at this point is zero, if this is the set of all the momentum points which are flat, and if this is the entire Brillouin zone, oh, what did I do? So one second, yeah, no, I have this. So if I look, what type of phenomena would we have where the entire Brillouin zone is flat and it's still quite interesting and actively currently researched? Then there would be two main topics. One would be quantum ferromagnets and flatband superconductors. You know, in a quantum ferromagnet, a classical ferromagnet is easily solved, but I myself was a bit surprised when you look at old research on quantum ferromagnets. I wouldn't have guessed there's still research done on ferromagnets, but apparently there is. So if you want an exact quantum instability into a ferromagnet, you actually have to work a little bit. And the way people did it in mathematical physics back then is they wanted to look for perfectly flat bands, because when the bands are perfectly flat, you can immediately imagine that if the system is at half filling and it doubles, it basically enters the ferromagnetic regime, it means that you don't pay any kinetic energy just by increasing the Fermi level, right? So an itinerant ferromagnet would always be a compensation of you pay kinetic energy, but you gain potential energy because all of a sudden all spins are oriented in the same way. So Pauli principle would disallow them from sitting on the same side. So that would save you potential energy. So this is one example in this diagram where we would say this is interesting, fields currently researched where the entire band is flat. There are also flat band superconductors. I don't have time to touch upon all of this. If you're interested, we can discuss that. I know what Rosa is working on. If there's some topic on this diagram that you like and that you work on, I can also say more words on it. It's just to give you an overview. The field connected to twisted materials that has now really resurfaced in a broader part of the condensed matter community is called fractional churn insulators. It's basically saying fractional quantum Hall effect in a band structure, so to speak. A Chern insulator is just the Hall effect in a band structure, and a fractional Chern insulator is just the fractional quantum Hall effect in a band structure. And that's what people are currently looking for in twisted materials, and they have observed it in twisted TMDs. That was a Nature article from 2 years ago. Another thing that's in another limit is a Van Hove point. And where I placed it is exactly flat, and it's not just decently flat. Here, I didn't talk about the y-axis yet. The y-axis is labeling how flat it is. So if I have a band that is quite flat, but not exactly flat, the derivative is not 0, but small. That would be this limit, but when it's exactly 0, then we're up here, and this is, for instance, where the Van Hove physics, the Van Hove singularity comes in. Would you know about a Van Hove singularity? Okay, I think that's easily interpreted, and it's unavoidable. If you ever look at band structures, if you do ab initio, you cannot avoid it. Van Hove was a mathematician, and in the 40s or 50s, and I forgot, 40s or 50s, he asked the following question. Say you live on a torus, and that's what you always do when you have a two-dimensional Bringer zone. You have two compactified dimensions, so the geometry that you have is a torus. Now put a continuous function on the torus. By continuous function, I mean you walk around the torus with a straight line, but the straight line has to come back to itself. It cannot end somewhere. If you do this, you will convince yourself, you will be able to convince yourself that you unavoidably undergo a point where the band structure does that. It's like a saddle point, right? This point is a Van Hove point. And Van Hove argued that this kind of saddle point is unavoidable in band structures. It appears on the square lattice. It appears on the Kagome lattice, and so on and so forth. It appears on the triangular lattice. So that's where Van Hove would be placed, because as you can see, if I have momentum here along the Bringer zone, that's k, this is finite, like del k epsilon is always finite. It's finite here and finite there, but only in this regime. This is where the dispersion and the velocity associated with the dispersion is 0. So that's why I placed it in this diagram up here, because if you have a Van Hove singularity, it's literally just one point that is exactly flat. So then maybe I will skip this topic because I spent more time on the introduction in order not to lose you on the subsequent slides. There's a phenomenon called higher order Van Hove. It looks like this. You get sort of shoulder features in the band structure. So what I mean is the difference is if I have a Van Hove, Van Hove would be this. Better. This is Van Hove, and higher order Van Hove would look like this. Right? So if this thing where it's flat is extended, this thing you might have not heard of so often because it is avoidable. The system doesn't need that, so it will try to avoid it. Whereas the Van Hove points are mathematically unavoidable, so any band structure has that. Higher order Van Hove is not necessary, but interesting if it unfolds. Kagome metals obviously are somewhere in this diagram because they have a couple of Van Hove points, and they also have some flat regions that certainly extend more than a few points, but they are not perfectly flat either. So that's why I placed Kagome metals here, and twisted flat bands and so on. We have, that's enough. But basically what I'm trying to tell you is, in all these fields that I just listed, flat band physics plays an important role, And actually right now, when you're looking into what condensed matter theorists work on, this covers maybe 80% of the field. So it is worth your time to think about flat bands and flatness in principle. And that's why let me move on to these three particular topics and mention them in a little bit more detail. I will start with the Kagome metals. I'll move on to the higher order von Hove points, and then I'll tell you a little bit about fractional churn insulators. Now, Kagome metals. I call it anomalous quantum distance. Would you know what quantum distance means? So when I have a Hilbert space and my eigenstates of the quantum system live in that Hilbert space, I can ask how much do the eigenstates change as I move along this eigenstate manifold? Is this sort of clear? So I take, obviously eigenstates are orthogonal, I understand that, but still you can ask the question, if I wiggle a little, so the Hilbert space is dense, as you know, so when I wiggle a little, how much do these eigenstates change as I move along in the Hilbert space? That is telling you about a metric, and this metric would be the quantum metric associated with the Hilbert space. If I now ask, how much do two states deviate from unity, like the bracket of two states, that parameterizes the quantum distance. And what I'll show you is that in the Kagome lattice and in the Kagome metals that, for instance, in Donostia are heavily researched, there is something that has to do with a quantum distance that explains all the phenomena that they see so far. But let me start simple, most elementary. We take a tight binding model on the Kagome lattice. Here you see the Kagome lattice, in case you haven't seen it before. These are corner-sharing triangles, and as a consequence, the Kagome lattice splits into three different sublattices, and I colored them red, blue, and green. So one single unit cell has three sites, and as a consequence, if we just assume that we don't have any orbital substructure, it means we have three bands. That's how the bands look like if you solve this problem. Everyone can do this in 5 minutes. You write down the matrix, the 3 by 3 matrix, because you have three sublattices, and what you will come up with is this band structure. Forget about this band up here. Would these two bands look familiar to you? They look like graphene. These two dispersive bands exactly look like graphene. Imagine we didn't have this flat band, then half filling would be exactly at the Dirac cone. So what you see is the Kagome band structure features two things that we already know from graphene. It features Dirac cones and it features von Hove points. These points that we talked about before. But on top of that, the Kagome lattice features a flat band. This band is mathematically flat. I should stress that. And maybe this comes to you as a surprise. These quantum tunneling amplitudes are high, like they can be huge, and still the Kagome band is flat. How can this possibly be? How can you have a flat band even though the electron can tunnel from one side to the other easily with a finite amplitude? The answer is that quantum particles are relate to wave phenomena, and you can have interference. And that's exactly what happens here. So if I take this particle, for instance, I can create an eigenstate that does not hybridize any further. I can create a localized state. And that is back in the 80s. This was done by a guy named Mielke in Heidelberg. What he did is he just looked at line graphs and characterized under which circumstances would lattices give away a flat band. And the way the calculation works, in case you're interested, it's not difficult, is you take a droplet of a lattice. By droplet, I mean you don't care about the boundaries, right? For the moment, you just stare at the lattice. And then you try to create these localized states. And once you do this, if you have n sites, you will notice that you will get n-1 local states. n-1 for n sites. You get 2 additional localized states by making a torus out of the droplet. I mean, if you make periodic boundary conditions, you need to enforce periodicity in both directions. So out of n-1 localized states, you get n+1 localized states. How many states do you need to fill one band? N. But you have n+1. There's one more that is at the same energy. Why I'm emphasizing this so much is, not only would the Kagome lattice have a flat band, the other bands also touch the flat band. And that's what I just explained to you. You have n+1 localized states, so this touching feature is actually fundamental. You can't tear the flat band apart from the dispersive bands. They are touching there, and if you want to tear this apart, you can actually do this. I don't know how you calculate your bands, or maybe you use Mathematica or so. Just put in a Kagome lattice and try to add a perturbation to the band structure that will split this flat band from these dispersive bands. That's a very educating exercise. Okay, it's now clear how the band structure of Kagome looks like. Okay, so why are people so excited about the Kagome lattice and the Kagome band structure? For many, many decades, Kagome would be typically associated with pyrochlor oxides. Herbert Smithite, maybe you heard this expression. What else? Capellasite. There are these weird minerals, right, that people give names to. Typically, these oxides would be in the Mott insulating regime. That's, for instance, something that Rosa Lopez also works on. So questioning what is happening to electrons when the interactions are so strong that the kinetic degree of freedom is frozen out, and instead all the electrons can only do is interact through their spin degree of freedom while they are localized. That's the Mott limit. That's the Mott limit of interacting electrons. Only in 2019 did people discover actual materials that feature a Kagome band structure and are metallic. So Kagome metals are very new. So you might think, when are there new discoveries in condensed matter physics and in particular in quantum materials? And I think this was one of the most exciting discoveries in the past 10 years, that they eventually found Kagome metals. I'm just telling you, why am I telling you all this? This is not an academic exercise. There are now materials which are metallic, whose structure looks like that. So it's extremely relevant to ask what type of quantum many-body physics will they give rise to. Now, I hope I can get this message across here. The thing, I was truly lucky there. I worked on the topic in 2012 when there was no such material. And I looked at it and I made some statements that then could be experimentally confirmed in 2022 that only relate to the single particle spectrum of the Kagome lattice and the eigenstates of the single particle spectrum. So far, everything I'm telling you, you can check on your Mathematica notebook and just play with the band structure. So let me show you what I mean. Let us take the Fermi level right at this Van Hove point. That's where I put the Fermi level. You should notice that this is not very far from half filling because we have 3 bands. Imagine, like, remember when you had graphene, the Fermi level would obviously be exactly at the Dirac cone level. But when you have the 3rd band, the Fermi level goes up for half filling. So it is somewhere slightly below this Van Hove singularity, but within reach of 10 MeV in the typical materials. So for the sake of the argument, let's place the Fermi level. It's a metal, you know, we can gate it and we can shift the Fermi level as we want. It's not an insulator. So let's say we put the Fermi level at the Van Hove singularity. then the Fermi surface looks like this. It's an hexagonal lattice, so the Brillouin zone is hexagonal. But on top of that, in this puristic way of just having nearest neighbor bonds and placing ourselves at the Van Hove singularity, it looks like a hexagon within a hexagon. So this is the Fermi surface. And you see the colors here. What I colored for you is, you remember that I told you I colored the sublattices in red, blue, and green. What I can do now is I can go to my band structure. I can take the eigenstate at this momentum, for instance, and then I can Fourier transform it and check how it distributes over the different sublattices. Is this clear to everyone? I get a momentum eigenstate, but the momentum eigenstate has a composition in terms of sublattices. I'm simply asking, where are you located? How much sublattice weight do you have on the blue, on the red, and on the green sublattice? And the interesting thing that happens is they are not equally distributed over the three sublattices. They change. And as I move along the Fermi surface, you see that this part of the Fermi surface predominantly are momentum eigenstates that predominantly occupy the blue sublattice. These are eigenstates that predominantly occupy the red sublattice, and these are ones that occupy the green sublattice. And that means the following thing, and maybe you can already appreciate this. I think, can you all see the other blackboard? So imagine for a second, I wouldn't have talked about the eigenstates. And all I give you is, this is my Brillouin zone, and this is my Fermi surface. And you would know that the Van Hove points are located here and here. And these are just by reciprocal lattice vector translation, the same ones. So this is the regime where the density of states is largest, because that's where the Van Hove singularity is. The density of states is reciprocal to the velocity, right? The velocity is zero here. That's why there are peaks in the density of states. If I now asked you, this is a metal, what type of scattering will happen? What's the dominant scattering? You would naturally guess that it would be scattering in between these Van Hove points. Yeah, right? So for instance, you would say that this is a good scattering vector, Q, right? And if you did this for graphene, by the way, this is the end of the story. This is the Q vector. You get antiferromagnetism, and then you get D-wave superconductivity in graphene. There's different stories about graphene. The problem in graphene is you can never reach this Van Hove point in realistic materials. You would have to dope too much. Like 13% of electrons, think about it, that's a lot of electrons you would have to dope into the thing to get graphene all the way from the Dirac cone filling to the Van Hove filling. But now let's imagine we can do this. Your natural assumption would be, okay, great, I have a Hamiltonian that is just some kinetic energy plus some Hubbard Q, okay? Fine. If I take this and I take this to be 1 and I take this to be 2, right? And I want to scatter in between them. I'm simply asking, what's the scattering between the state here and the state here with a local Hubbard U? And typically, this is the biggest interaction scale in the system. And these are momentum eigenstates. They overlap. But do you see what happens here? This guy here is, I just stick to this, is blue. And this guy here is green. So when I look at this matrix element and I Fourier transform back into real space and I see this state only lives on the green sublattice and this guy only lives on the blue sublattice, the local Hubbard U cannot connect them. Is this clear? Because a local Hubbard U would need a state to overlap on one side together. But one guy here only lives on all the blue sides at the same time, and the other guy lives on all the green sides at the same time. This matrix element will be close to 0. And if I take this as a sign, that is what people call quantum distance. Like these two states are infinitely apart from each other in the Hilbert space. At least they can't be connected by a local operator, such as local Hubbard U. Is this, can you appreciate that? So the eigenstates here, they distribute over different sublattices. The largest density of states is located at the M points. Naturally, I would be looking at the scattering channels connecting these M points. And I would find here, however, that if I take local Hubbard U, I cannot connect them, no matter how much density of states there is. That is what I called sublattice interference back then in 2012. And I'll skip this. I don't want to overburden you with stuff. What really matters to me is that you understood what the argument here is. And I'm happy to go over it again. Yes? Yeah, so maybe I should forget about this. So quantum distance and quantum geometry are these new words, and honestly, they are a little bit overcomplicating things. Basically, what they are saying is your Hilbert space in quantum mechanics. It's a ray space, right? It's projective, like two states that differ by a phase are still the same. So there's a little bit projectiveness in the Hilbert space. I simply want to ask, how can I reach from one eigenstate in the Hilbert space to the other? How are they connected? How are they connected? And the initial Hamiltonian is H naught. That was a free non-interacting electrons hopping on a lattice. It was not contained in there. That's correct. And if you stick to that, in a strict sense, all the states are infinitely away from each other because they are different momentum and what do you want, right? I get that. The quantum distance argument becomes relevant under different circumstances when you ask, given some sort of perturbation or some sort of matrix element that you would allow yourself to use in order to couple two states, how big is the matrix element between the two states? That's totally fine, but as you know, the interacting many-body problem we can't solve exactly. H naught we could solve exactly. This we know exactly. So when we know something exactly, the natural thing would be we stick to what we know exactly, and then we slowly add the stuff that we don't know exactly and try to understand it. So that's why I said, let's try to understand the effect of this Hubbard U from starting from the non-interacting Hamiltonian and then adding the Hubbard U. That's what people always do, perturbation theory. All the numerical methods try to deal with the fact that the interacting many-body Hamiltonian is not exactly solvable. So most of condensed matter methods revolve around this fact and try to make progress towards getting as close to the exact solution as possible. Okay, so that is what is special about the Kagome lattice. That's what I had found in 2012. And it was confirmed experimentally, so people could see the nature of these Van Hove points to occupy different sublattices exclusively. That was done with polarized ARPAS experiments by Ricardo Comin at MIT. I'll skip this, but what I just quickly show you is basically picking up on what you said. Let's say, what is the expected quantum phase diagram for the interacting Kagome metal? So we have the Kagome metal H naught, we add interactions. This time I not only add local interactions, I also add nearest neighbor repulsion. Typically, people call this V. You can call it whatever you like. So in this UV model, what you find is that this is the phase diagram. And I will not get into details. What I want you to appreciate is why this I called it sublattice interference in 2012, why this explains the phase diagram. And for that, I would rather like you to remind yourself of what happens on the square lattice. That's easier to understand because you've seen it more often, I assume. Where's this thing? Yeah. So now that you appreciated what happens on the Kagome lattice, let me go to the square lattice. And here, let me look at the Hamiltonian.
You may say what the colors means. The yellow one.
Oh yeah, that's the critical temperature, like how high is TC or the nail temperature or whatever, you know, at which temperature does this many body phase settle in? There's way more on the slide than I have time to discuss. My main emphasis should be on that you get one full story, that you understand how does the Kagome lattice band structure relate to the quantum many body phases that people see. That's my main focus on this talk. I noticed that that's probably more efficient here. So that's why I slightly switched the talk, in case you've noticed. So U and V, so when I only have Hubbard U on the square lattice, what will happen? Would people know that? This would be, at half filling, this would become an antiferromagnet, typically, right? When I increase V, so let me just draw a line here, and I take U over V, and that's infinity. So I will come from an antiferromagnet, and now I slowly increase the nearest neighbor repulsion. Have you ever done this in whatever mean field theory? Would you know what happens? The system switches into a charge density wave. So then it will look like a checkerboard lattice. Have you seen that? So when I increase, if at some point, what will happen is the system will develop a checkerboard lattice, which means that it will have double occupancy on the sides that are just turned with a circle and zero occupancy on the sides that I didn't encircle additionally. The reason is simple. They don't pay nearest neighbor repulsion under such circumstances. Do you all understand that? So when V becomes bigger, right? When V becomes large, this is a more stable arrangement of the charges, because then if I have two charges here, the neighbors are empty, so I don't pay nearest neighbor repulsion. Okay? It's a standard intuition from the square lattice that if nearest neighbor interaction is increased, then the charge density waves should dominate over the spin density waves, over the magnetism. Exactly the same thing happens in Kagome. Because of this matrix element effect that I just explained to you, this certainly does not apply to V, right? Because nearest neighbor interaction, let me come back to this slide, this matrix element effect, I had the example of the green and the blue guys, right? They are certainly neighbors, so they can couple by nearest neighbor interaction, but not by local Hubbard use. So what does happen at the Kagome lattice? This sublattice interference that I just explained to you will artificially enhance the relevance of the nearest neighbor repulsion. And so what happens in the Kagome lattices is exactly what you would get on the square lattice if you were to increase the nearest neighbor repulsion. The charge order will predominantly win over the spin orders. There's there's not much magnetism, but there's a lot of charge order. And after 5 years of very intense experimental effort, that's exactly what has been found in the Kagome metals. And again, largely also by people in Donostia. The talk has been going on for around 40 minutes. I don't want to overburden you. Would you be more interested in pushing this higher order Van Hove thing a little bit further? Or would you like to hear a bit about quantum geometry? Rosa, what should we? Quantum geometry, let's go there. Let's go there. Yeah, and for that, let me just, so 1 second. So this looks technical, but let me try to get you through this. It would be worth your time. So quantum geometry works like this. First of all, the expression is a bit strange, but you'll appreciate in a second. Have you all heard about Berry curvature? Right? So how is Berry curvature basically explained? You take, that is the best, that's the most elegant closed form expression that I would have for the Berry curvature. You can choose whatever you like, but let's say you have a Hilbert space and you have eigenstates of the nth band. The n here as an index just means we're looking at the nth band. So for the moment, you can also just erase the n for your mind if it's confusing you. Just forget about the n. The q is 1 minus the projector on the eigenstate. So the q basically measures how far you are away from unity, right? So when you're putting the phi n in there, the q gives you 0. So any finite amplitude here is making a statement, you're deviating from this eigenstate phi. Is this clear? That's what q means. Now, you see something weird here. You see derivatives in the eigenstate. Maybe you've seen this before. These derivatives mean that I slightly, for instance, I take momentum space. If I take momentum space, that's our space, right? And I take this point, this point is k, and I want to move it just a little to the other point, k plus dkx, for instance, right? Then I would write it del kx of k. I would ask, I take the eigenstate at k, I move an infinitesimal amount along kx, and that would be the eigenstate, and I would abbreviate it by del xk. That should explain the notation of this partial I phi. And again, this n is just for completion because you would need to assign this to every band. You heard about the Berry curvature, you can assign this to every band, so you need a band index, right? So that's why I kept the n here. Now, this state is just, this thing is just making a statement. If I take the matrix element of the n-type projector onto the eigenstate phi and I move the phi a little, what is the result there? And this result is an amplitude in quantum mechanics. It can have an imaginary part and a real part. The imaginary part is exactly what you know as the Berry curvature. So the Fij is exactly the Berry curvature. So if this amplitude is all imaginary, then all you have is the Berry curvature. But if this amplitude has an imaginary part and a real part, then you don't only get the Berry curvature, but you also get what people call the quantum metric, the quantum geometry. And that's why I wanted your attention for 2-3 minutes on these two expressions, because they are by far, I would say, the most mathematically elegant and condensed way of looking at this. Because then notations in Berry curvature differ and do this and that. This is what do you do in Berry curvature? In Berry curvature, you hate these expressions because they are not gauge invariant. So what you'll do, as Berry did in his paper in 1984, he goes into energy eigenstates instead of momentum eigenstates. You get rid of the Berry curvature ambiguity from the phase ambiguity of Hilbert space elements. But here, what I like about it is it's absolutely elementary, and everything that you need is written here. Because these indices get inherited here, so the Berry curvature, in principle, also has an according matrix structure with respect to the dimensionalities of the space you're living in. So that's why it carries the indices ij, and that's why you can also appreciate why this is called a metric. You know, it's in a two-dimensional lattice, it would carry the indices 1 and 2, or x and y, whatever you call it, and accordingly, this is a 2 by 2 matrix, and this is a 2 by 2 matrix. That's the Berry curvature. That's what people call quantum geometry. And why did people talk about it so much? So first of all, it is nothing complicated. It's mathematically very clear what's happening, but people liked the Berry curvature for many decades. They didn't talk much about this term. And there's two answers to that. But before I come to this, let me just appreciate this expression and bring it into a convenient form that you might have seen earlier. So some people also like to write the Berry curvature in terms of a Berry potential that Berry in his paper from 1984 calls A. So if you want to connect it, that's exactly how it should look like. The Berry connection in my notation would be minus I bra of phi ket partial j phi. That's the Berry potential. That's the Berry potential. And then the Berry curvature gets the antisymmetric form that you would also know from electromagnetism. And then you rediscover the statement that you probably heard, that Berry curvature, Berry flux monopoles act like charges in momentum space. That's what they are. So they are really like the formalism of Berry is invariant under it looks form invariant to electromagnetism, but the Berry charges live in momentum space and the electric charges live in real space. It's all the same. That's why people liked to use these potentials. When you do this, and that's your definition of the fxy, I already put the two-dimensionality, and that's the fxy. The quantum geometry looks different. The quantum geometry is the real part of this antisymmetric combination. Sorry, the J must be here and the I must be here. I'm sorry for that. And yeah, and then this expression, to finalize on that, this is really what, if you ever looked at geometry in your math class and so on, this explains to you why this is called quantum geometry. For this, let me answer your question in a slightly different way. If I look at the differential, or the distance, the distance between a momentum state at k and a momentum state at k plus dk, what I want to look at is the trace of unity minus the product of two projectors, one projector on k and one projector on k plus dk. So this really measures how far do the states change as I shift from k to k plus dk. And then you can write this in this closed form, and that you would know from special relativity. That's exactly that's the metric expression. If you have a Euclidean matrix, we always forget about it because it's 1, 1. So this would be gone. You would only have dkx, dky. That would be the infinitesimal element of integrating over momentum space. But since now we have we have potentially something interesting. Actually, the true Hilbert space structure of the distance between a state at k and a state at k plus dk is, strictly speaking, not dki, dky, dkj, but gij, dki, dkj. Hopefully you remember that. So when I have x mu, x nu, you would know that from special relativity. That's the expression. That's the norm expression in special relativity, and that's exactly how it looks like. So that's a little bit of a mathematical slide, but what I'm claiming is, if you ever come across the expressions quantum geometry, Berry curvature, again, come back to your Mathematica notebook. That's what I like about it. You don't need many body physics. You can study all this just from a band structure on your Mathematica notebook. And yeah, this is, I claim, this slide is all you need to know mathematically, and then you start evaluating the expressions. I know I'm running short of time. I would have liked to tell you more about it, how complex geometry helps to optimize the quantum geometry here. So people are now excited. Let me finish by a more broader statement. This thing should have been on everybody's watch for 40, 50 years. People always thought it's very small. Why did people think it's small? This quantum geometry, to people in the room that do many body physics, it smells a bit like a self-energy, like a real part self-energy component. It just changes the dispersion a little, right? And it's small, people thought, against the band structure. But if you have a flat band, the bandwidth is 0. So all of a sudden, the quantum geometry is the dominant term that assigns a bandwidth to your problem. And that's the reason why people nowadays talk more about quantum geometry. It's typically assumed to be a small effect, and this small effect people didn't care about. But in the flat band limit, people do care about it. That's the last thing I want you to understand. Maybe in order to complete your understanding of everything here, why did people like the Berry phase before? That's easy to understand. In many observables, like Hall conductance and so on, there is only a term that the leading term is proportional to the Berry term. So when the leading term of something observable is related to the Berry phase, everyone was sensibilized towards not suppressing the Berry curvature. You know this from perturbation theory. If it's a leading term in an observable, you don't care how small it is. You carry it with you because it's the leading term. That's why people liked the Berry curvature more and knew it all along, and basically put the real part a little bit under the rug. That's really what happened. And if you want to know more about it, you just Google quantum geometry and review, and there's a couple of interesting reviews on it. The mathematical content, all you need is on that slide. And maybe for today, maybe I'll conclude with this, and thank you for your attention.
Okay, thank you for the nice talk. And now maybe someone has some questions or something. Yeah, please.
Maybe could you explain the effects of the quantum geometry in example like fractional quantum Hall, 1/3, because that's what I'm more familiar to.
Okay, so the most drastic effect so far for quantum geometry has been predicted for flat band superconductors. I come to fractional quantum Hall effect, but let me tell you the most drastic effect in flat band superconductors. In flat band superconductors, naively you would think that different Bogusław quasiparticles can't talk to each other because they are localized. This quantum geometry gives them a way to actually connect to each other. And that means that many transport quantities in a flatband superconductor will have as their leading term the quantum geometry. And that's why people are so crazy about this stuff, because there, after all, you could measure the quantum geometry, because the leading term of this observable, like diamagnetic currents and so on, the leading term in a flatband superconductor would be the quantum geometry. Measuring the quantum geometry in other contexts has not been possible. Let me be very frank. It's very hard to isolate a quantum geometry term in an actual experimental measurement, because there can be all sorts of things that come together, like self-energy effects. Just conventional self-energy effects will overwhelm the quantum geometric aspect. For fractional quantum Hall effect, the quantum geometry has a much deeper emergence. And that's something that Duncan Haldane has been working on in the past years. He never called it quantum geometry, I believe, but it is quantum geometry. He claims, and supported this, and people are agreeing on this, that in fractional quantum Hall effect, the system chooses its own new non-commutative geometry. And for that, I need to check whether you know the guiding center coordinates and the Gervin-Platzmann-McDonald algebra. Have you heard of this? So from the late 80s. So the point being that if I'm an electron in a fractional quantum Hall effect and I attach fluxes to myself, right? I have, let's take 1/3, the Loveland state. I have 3 times as many fluxes as I have charges. So one single electron should attain 3 fluxes. The resulting orbit that follows from this, if this moves along, it sees a different geometry. It doesn't see simple, flat Euclidean space. The geometry is altered, and the altering can be reconciled by a quantum geometry term. Now, this quantum geometry term, you cannot calculate the way I did, because the eigenstates of the fractional quantum Hall effect are not band structure eigenstates anymore. Where is it? This thing here cannot be evaluated easily for fractional quantum Hall effect, but you can get to the expression if you follow the line by Duncan Haldane in the last papers of his 3-4 papers he wrote in the past 4 or 5 years. And so it's an important question you raise, but unfortunately, it is super important in fractional quantum Hall effect, but the way you reach it will go through a lot of depth before you eventually arrive at it. So you first need to appreciate what the effective quasi-particles are in the fractional quantum Hall effect and what type of geometry they attain. And once you appreciated this, you can rewrite it as a quantum geometry problem, and then you do get a quantum geometric point. Now, since you asked that, let me even add one more thing. I don't like the expression quantum geometry. This is something by which you can look it up by the expression quantum geometry, but there's something I don't like about Berry and quantum geometry in the way it is described in the literature. Both expressions don't know h bar. If I send h bar to 0, the expressions stay exactly the same. So I think that's an important lesson to be learned. Whenever you have a Hilbert space, you can have this geometrical term. Whenever you have a Hilbert space, you can have a Berry curvature. Hilbert spaces appear in quantum mechanics, but they also appear in classical systems. All you need is a vector space with an assigned scalar product and so on. You know the rules for a Hilbert space. That's what you need. As soon as you have that, you can have Berry curvature and you can have this geometry term. And I also happen to work on classical systems, electric circuits, where I try to mimic Berry curvature and so on and so forth. So actually to measure quantum geometry, I'm pretty sure I'm currently working on a project that's nearly done. I want to measure this quantum geometric term in an electric circuit network. And it is true what I'm saying, but then people will say, hold on, electric circuits are not quantum. What is quantum about it? They are classical, but so is this. This expression is all classical. It just so happens that it is relevant in a quantum mechanics context because we unavoidably have a Hilbert space. But please keep in mind that Berry curvature and this geometry term can be relevant in any classical system that has a Hilbert space. And the essence is it relates to phase space and not to, it relates to parameter space and not to phase space. The difference between a classical and a quantum system lies in phase space, where the h bar gives you the coarse graining of the space, right? Like delta x, delta p is 2 pi h bar to the dimensionality, that you have a coarse graining in the quantum phase space. That's not it. This is about parameter space, and this thing doesn't care whether it's quantum or not. That's another thing I wanted to stress. Okay.
Okay, so no more questions. I think that we can stop here. So thank you very much, and you will have another opportunity to hear him in another seminar at the IFIS seminars, the next 6th of October. Okay, thank you very much.
More classical electromagnetism.